Annyeonghaseyo. Hello, and thank you so much for this opportunity to present our interim stage of our KAIST KC30 project, Computer Science of Continuous Data. Let me start by sharing the screen and then jump right into the overview of this talk. I will first recall the research background and necessity, then summarize the results and achievements so far the past 30 months, then report on work currently in progress and how that translates into future plans. So let's dive right into the research background. The motivation is that we want to remove the discrepancy between hardware and mathematical data types, because this discrepancy often gives rise to programming gaps. For example, some of you may remember the old computer game Civilization from the late 1980s, 1990, where the human player governs a country of his choice from the development from Stone Age to the future, and the other countries, neighboring countries, are controlled by a non-player character, a kind of early stage AI, where each leader is described by some numerical parameters. For example, India is governed by Gandhi, who has a very low aggression parameter 1. And one of the rules of the game is that during the course of time, when country develops democracy, its aggression level decreases by 2. So the programmer had intended that this decreases aggression, but when the data type is a byte as opposed to a mathematical integer, then a wraparound occurs, and actually the aggression level of Gandhi increases to 255 and starts waging war against its neighboring countries. Now, this is a kind of an anecdote, but the background is programming errors to the discrepancy between mathematical and hardware data types. And this is true for the discrete setting of bytes, different from integers. And this is also true for the numerical setting using floating point or double precision numbers as opposed to mathematical real numbers. For example, floating point numbers violate the associative law and the distributive law, not to mention rounding error and their propagation. And that's why this famous book series is called Numerical Recipes as opposed to numerical algorithm, because as I teach in my class, algorithms must be correct as opposed to heuristics and recipes. And indeed, this leads to bugs with sometimes disastrous consequences. For example, the Ariane 5 maiden flight failed due to a numerical bug, and also the Sleipner oil platform turned out to have a design flaw because it was designed using unstable numerical code. This can be prevented by having data types that agree with the mathematical data types, and modern high-level programming languages, for example, support real mathematical integers. Java does, Python does, and C++ can be extended to do that using the GMP library, object-oriented programming, information hiding, and the same can actually also be done for continuous data types like real numbers, real vectors, and real polynomials. And I will, this is exactly the topic of our research. So abstraction, hiding all the implementation details of exact mathematical data types has benefits, and that starts on the low level. You don't need to know basics of quantum mechanics in order to program your computer, although quantum mechanics underlies the transistor. Transistors are combined into CPUs, and CPUs are combined to motherboards. Then all these details are hidden behind the BIOS, the device drivers, operating system, object library, and high-level programming languages. And this allows our high-level programs to run on any kind of computer with a PC or a laptop, on any kind of operating system. So abstraction has all these advantages, and we do the same for continuous data types. So our project has been running for 30 months. In this time, I've been a member of program committees. We have had two major journal publications and three major conference publications. Currently, we have written 3 technical reports of work in progress that will turn into publications later. We have had many members in our lab, students from abroad as well as domestic. These are our current lab members, and we collaborate with Dr. Stoiminov. We had an intern from Vietnam, and we are a member of the new EU Horizon exchange project. I will elaborate particularly on the publications at the end if there's still time, but for now let's move on to work in progress. So the technical reports, first technical reports is interdisciplinary about computational knot theory in combination with our paradigm of exact real computation, conducted by a master student Jaden from United States and co-advised by Dr. Stoiminov from Dongguk Dae. So here you see Alexander visiting our lab in the N1 building. The second technical report is about new approach to parallel processing, an extension X of the Pluto technology, a new architecture developed by the intern from Vietnam. Its architecture is a kind of a counterpart to the von Neumann architecture. And the third technical report is on parallelizing to accelerate Picard iterations using either GPU parallelism or multi-core CPU. And Sehun has explored how much acceleration is feasible and where no further acceleration benefit comes in. So this is work in progress, and I already mentioned the EU Horizon project, which consists of 8 members in the EU and 9 members outside of the EU. We're one of the participants outside of the EU. The members in the EU are funded by the European Union. Those outside must get their own funding, co-funding. We have applied for co-funding at NRF, but unfortunately our application was rejected. So we will need to try again in order to fund the exchanges in this project. So this is a work in progress, and now future plans. In future, we want to continue exploring hardware acceleration approaches to function processing, like FPGA. We want to determine the computational complexity intrinsic to partial differential equations which live in Sobolev spaces. And we want to continue reviewing problems from within pure mathematics, such as knot theory, from the perspective of our paradigm computer science for continuous data, and participate in the EU project collaboration and exchange. And KC30 is an important financial safety net, a baseline, in order to guarantee the stipend for our lab students. In the long run, we want to develop a computer analysis team. So when I was a master student, I was part of the MIPAT team in Paderborn developing a computer algebra system, but computer algebra is for algebraic problems, not good for analytical problems. IRAM is good for analytical problems. It supports this real data type, mathematical real data type without rounding errors. Also real vectors, matrix, polynomial sequences, and analytic function. We have extended this. You can download this in our extension from GitHub. In the long run, we imagine a new revision of IRAM 3.0 and that can process continuous and integrable functions efficiently using hardware acceleration. And all this will hopefully lead to a computer analysis system. So to conclude, I've talked about research background, I've summarized results and achievements so far, work in progress, and future plans. And if time permits, then let me now elaborate on the 5 important publications we have achieved. So first is in the journal Logical Methods in Computer Science. Here we develop semantics and specification logic of this paradigm exact real computation. Let me skip over the abstract and illustrate the gist or the motivation. I mean, it's numerical folklore, not to test real numbers for equality. So what can you do then with these real numbers? Can you compare them for inequality? If we can use inequality, then Boolean combination allows us to recover equality, so no inequality either, nothing. And we've resolved this paradox by devising a partial multivalued semantics for real inequalities using Kleene ternary logic. Here you see the truth table for this ternary logic, and that is then developed into a full-fledged denotational semantics in this paper. Second journal publication in the ACM is a quantitative coding and complexity theory of continuous data by our PhD student Dong-Hyun Lim. And again, let me skip over the abstract and just emphasize that this is kind of a continuous counterpart to the Claude Shannon's famous discrete quantitative coding and complexity theory, like, you know, the Shannon's famous sampling theorem, for example. We've also developed kind of a dictionary between quantitative and qualitative. The qualitative setting is well established. Computability, we devise a counterpart complexity. Qualitative is topology, quantitative is metric, and so on. Moving on, conference publication. Here we have initiated the study of software testing in computable analysis. Fourth publication is a second-order parameterizations for the complexity theory of integrable function, which extends the well-known parameterization for the complexity theory of continuous function, but integrable LP functions are what underlies modern partial differential equation theory. So that's a conference publication. And finally, degrees of second higher order polynomials, again with Dong-Hyun Lim, generalizes linear, quadratic, cubic, and quartic polynomial running time or general growth from the first order to this aforementioned second order setting. Basically, turns out that the degree of a second order polynomial is not a number, but it's a first order, an ordinary polynomial. Now we have two kinds of composition and they translate in different ways. Third order polynomials, their degree is a second order polynomial, and one has 3 kinds of composition. And yeah, this is all worked out in detail in this publication. So that's all I wanted to say. I'm running out of time, but now I'm available to answer your questions. Thank you very much.